Hello everyone, welcome back to the channel. In this video lecture we shall solve this problem coin change. In this problem we are given an integer array coins which represents coins of different denominations, and we are given an integer amount which represents the total amount of money that we want to generate. We have to return the fewest number of coins or minimum number of coins that we need to make up that amount. Okay, so we want to make that amount and we want to use minimum number of coins, and one coin can be used multiple times. If we cannot generate the given amount with the given coins, then we would return -1. Okay, so that's the problem statement. Let's see the input and output format. In the input will be given an array of coins, okay, and an integer amount, and at an output we have to return the number of coins that we require to generate that amount. For instance, in this example 1 to 5 is the array, so we have 3 coins. We have 3 types of coins, so these represents the types of coins. The first types of coins is of value 1, the second type of coins has value 2, and the third type of coin has value 5, and we want to generate amount 11 here. Then one of the ways to generate that is to use the coins, 2 coins of type 3, that is 5 plus 5, so it will give me a value of 11, and 1 coin of type 1, type first, and that will give me a value of 11. So that's how I use 3 coins to generate my target amount, and that's the fewest number of coins that I can use. Okay, I'll show you why this is the minimum number of coins in my next slide. But before that, let's see the constraints of the problem. The length of the coins array, it goes up to 12, so we have at max 12 type of coins, while the value of each coin may go up to 2 raised to the power 31, and the amount goes up to 10,000. So at max we have to make an amount of 10,000. Okay, so let's better understand the example. So this is the example coin. We have given coins, 3 types of coins, amount, and we want to generate this amount using these type of coins, where we have each coin where we have infinite numbers of coins of each type. So we have infinite number of coins of value 1, infinite number of coins of value 2, and so on. So let's see the possible ways to generate 11. So one of the ways to generate 11 is basically use the coin 2 5 times. 2 plus 2, use it 5 times. Okay, 5 times, and that will give me a value of 10 plus 2, and use coin 1 time, so that is giving me 11. Another way is to just use these coins of value 1 11 times, and that will give me a value amount as 11. Another way to do so is use, let's say, 3 2s, 3 coins of value 2, that give me 6, and 5 coins of value 1, that will give me 11. So there are a number of ways to generate this amount, fine, but this, if we construct the amount in this way, I'm just using 3 coins, 5 5 1. And why I'm guaranteeing that this will give me minimum number of coins to generate the final amount? Because observe that I'm using denominations of largest size. Okay, so these are the denominations of largest size. That means it will give largest value, so that's why I have to use less number of coins. So this is the minimum amount, this is the minimum number of coins that I can use, hence the answer is 3. Okay, so this may lead you to some greedy approach. The greedy approach is simple, that is, we're given some amount 11, let's say some amount, let's say A, and greedily what I can do, since I want to minimize the number of coins, I start from the coin of largest size, or the coin which imparts me the largest value. For that I can sort the coins array. In this case it is already sorted, but in case it is not sorted, then in the greedy approach, let's say I sort the array and I know that the last value is the largest value, and I just try to subtract that value from this from the given amount, or try to construct the given amount from the value which is present at the uh, right side of the array. Okay, so what is the problem in that case? The problem is that we cannot always generate the required amount using the largest value. For instance, in this case I used the largest value 2 times, 5 plus 5, but then I have to use 1. I cannot use 5 again because that will give me 15, so I had to use 1 here. But suppose 1 was not present in this array, so just imagine that the array would have been 2, 5. In that case, if I try this greedy approach using the largest value coin, then after using 2 coins of this type, I will have the required amount as 1. That means I require a coin of value 1 to make my amount 11, but I do not have that type of coin. The smallest coin that I have has value 2, and that will give me an amount of 12. So it is not possible to generate the given amount using the greedy approach. Okay, that means greedy approach is not always right, it is suboptimal. So I have to improve upon it. Let's see how I can think about this problem. So let's see how we can solve this problem using another approach. The greedy approach was suboptimal. Let's build a better approach. Assume that the amount is A that we want to generate, and this is the final set of coins that we will get. So this will contain the final coins that we will require to generate our amount 11. Fine. So this is A. So assume A is the amount that we have initially, and we are standing at first index here. So I'm present here. Okay, so I have two options while I'm standing here. Either I use this coin in my final denomination, or I do not use in my final set, or I do not use this coin to generate my final set. So if I use this coin, then the remaining amount that I want to generate would be A minus 1. Otherwise it would be A. Okay, in this case, this is the case when I do not use this coin, while I just move to the next coin here. So this is the case when I have moved to this coin, and this is the case where I have used this coin. Okay, so here I would contain 1 in my set, and here I will have empty set. Okay, here again I would have two choices. Since I'm standing here, I would have two choices: either use this or do not use this. So here I would have two choices: A minus 1, minus 1. I can use 1. I can use 1 because the amount that is remaining is 10. So definitely 1 can be used to generate this amount, because the value of this denomination is less than the value of value that we required, the amount that we require. Okay, so that's why I can do this. Another case is simple. I do not use this coin, rather I use this coin now. So that means I simply move to this index. So now I'm standing here. So this has a set 1. This set contains 1 only, while this set contains 1, 1, 2 times, and this is empty. And now I will have two cases here. I use the coin on which I am standing, that is coin number 2. First I have to ask, can I use this coin to generate my amount 11? Yes, I can, because the amount is 11 here, and 11 minus 2 is greater than equals to 0. Hence 2 can be used to build 11. Fine. So that's why I can use this coin to build my amount 11. So now here the set will be having value 2, and the remaining amount is 9 here. Okay, another case here, I skip this denomination as well and move to this denomination, the coin third, the coin number 3. So in that case a stays 11. Okay, so that's how I'm generating my sets. Okay, finally here again I will have two choices, here again I will have two choices, here again I will have two choices, and so on. So all at each level, at each state, so for any amount here where I am standing, I have to check whether the remaining amount here the remaining amount is 10, here it is 11. If that amount is greater than or equal to the denomination on which I am standing, if it is, that means the coin on which I am standing can be used to build. It can be used, it is not definite, but there is a possibility that it can be used to generate the amount that I want to generate. Okay, so I build two cases, either I use that coin or do not use that coin. Fine. So that's the logic, that's the approach to build the solution for this problem. Okay, so let's see how we can solve it. To imagine a function coin change here. This function takes in the index, so this index corresponds to the index which is pointing to the array coins. So initially this index is 0, and the amount variable, so this amount variable corresponds to the initial amount that I have. So initially it is 11. For this case, this function will be called at index 0 and amount 11. So what it is saying, okay, start from first index here, use this array 1 to 5, try to generate this amount from this set of coins. Okay, so this function basically gives me the number of coins that I can use of these denominations starting from index 0 to n-1. So these are the denominations that I will be given, and I have to use these coins, and how many coins I will have to use to generate my amount 11. So that's what this function will return to me. Okay, so how will the body of this function look like? So I want to know the body of this function. For that, I know that if initially index is 0 here, then this function is called, and in the next step inside this function I have to call this function here on the same index 0, while the amount will decrease by 1. Why? Because I have used one coin of denomination 1 of this type, okay, of first type. So I've used the coin of type first, and due to which the amount has been decreased by the value of the coin that I'm using, and the value of the coin that I'm using is 1. So that's why I'm decreasing the value of the coin from the amount that I have. Okay, this is the one way. Another way, I do not use this coin while I jump to the second number coin. So here I'm saying, okay, maybe the final set will contain the first coin, okay, as one of the coins which are being used to generate 11. While here I'm saying, okay, I'm not using 1 here, rather I may use 2. So in that case I will call the function at index 1. Here the amount stays the same. Okay, here you see the amount is still 11 and I'm not using this coin. Now the set that I have is 2, 5. Fine. So here I can just use coins of denominations 2 and 5. Okay. So similarly, that's why I'm not incrementing this by 1, because I am not using any coin here. Similarly here, since I'm standing at 0, so there will be two cases. If I so first I will ask, can I use coin number 0 or coin number 1 here, which has value 1, to generate this amount 11 minus 1, which is 10? Yes, because 10 is greater than 1. Therefore 1 plus CC 0, 11 minus 1 minus 1. Okay, I have again used this coin, so now the set will have 1 1. This is the set that I have till now. While the second case can be, okay, I have used 1 here, now I don't want to use it, I want to move to the next coin. So in that case I move to this index, while the amount I decrease by 1, and so on. So that's how I am proceeding. Finally here I will have subsets. Finally I have some functions where this amount will become 0. That means I have generated my amount, and corresponding to that amount I will have some set prepared, which will have some number of coins. Then out of all those sets that would be prepared as a result of these function calls, I will return the size of the set which is smallest. Okay, and that's all we have to perform in this task. Okay, so let's see how will the body of this function look like. You can see that for each index I will have two function calls. Okay, but for that I have to check one condition, that is if the given amount here is greater than or equal to the value of the coin which is present at this index. If it is, then I can use that coin to generate this amount. Okay, hence I call this function two times. So this is how the body will look like. So see here, the function is called at index 0 and amount initially is 11. Okay, and first I check whether the value of the coin at index is less than the amount that we want to generate. If it is, that means I can use this coin to generate this amount, and hence I call this function for that index by using that coin which is present at this index. Here since I'm using this, the amount decreases by that value, and since I'm using one coin, I have to increment the number of coins by 1. Now this function call will give me the number of coins used to generate this amount, and hence this will return me the number of coins to generate this amount. While there can be two cases, another case is, okay, maybe using this coin will not give me the minimum number of coins, while not using this coin may give. Hence I'm calling this function on the amount and expecting that maybe for the next set, like starting from index 1 or idx plus 1 to last index, maybe I will find some subset there to generate my amount which would be lesser in size. So that's what I'm doing here. But there is this case when the amount that we want to generate is less than the value of the coin that we are standing. Simply, if the amount that we want to generate is less than, let's say the amount would be let's say 4, amount remaining is 4, and we are standing at coin number 3. You see this coin has value 5 and the amount that we require is 4. Hence we cannot use this value to generate 4. Therefore we call this function again on the next index. So that's what I'm doing here. Okay, so this is the idea. That's how we solve this problem recursively. Okay, so let's see the recursion tree here. So this is same as I drawn here. At each function I'm calling two functions. Okay, if the value of the coin is less than the amount. Otherwise I'm just calling the function on the next index, not using that coin, because that coin cannot be used. Fine. So let's see how let's analyze the time complexity of this code. Okay, so before that, let's see what is the base case here. See, in the base case, we see if the index has crossed the array, that means the last index of the array, or the amount that we want to generate is 0. That means we have generated our amount that we wanted to generate. In that case, I will not use any other coin to generate 0. Hence, I am returning 0 here. So if the amount is 0, I no longer need any other coin for the amount that we have. Okay. Otherwise, if amount is not 0, okay, amount is not 0, so I'm assuming that if the amount is 0, then this is going to return 0, and then if I'm executing this line of code, that means amount is not 0. And if the amount is not 0, then that means I have reached the index, the last index, or I have crossed the last index, so I have reached n. In that case, I will return 0 because I have no solution for that. That means I cannot generate the required amount with any type of coin. So that's why I'm returning 0 here. Okay, so now let's see the time complexity for this code. You can see that at each function call, it is recursively calling at most 2 functions, and hence the branching factor is 2, while the height of this tree may goes up to the sum or the amount that we require. Because imagine the worst case, to analyze the time complexity, imagine the worst case. The worst case would be, let's say we want 11 here, this is the case, and the denomination, the number of coins that we have, or we have a coin which is of value 1, which we have here indeed. In that case, I may decrease the amount. I may keep, so here, okay, in that case I may keep on decreasing the amount by that coin. So that will give me 1 plus 1 plus 1 plus 11 times equals to 11. So this is costing me 11 function calls. Okay, so it is calling me 11 function calls, and hence 11 as the height of the tree. So this, observe this branch here. You see 11, 10, 9, 8, 7 and so on. So this will have a height of 11, which is the amount. So hence I will have the time complexity as 2 raised to the power amount that we require, and the amount that we have can go up to 10 raised to the power 4 or 10,000, and the 2 raised to the power 10,000 is a very bad time complexity. It will give me TLE. And hence this solution is also not an optimal solution. We have to improve upon it. Okay, so now for that, we know that this is a recursive solution, and if we find that there are optimal substructure and overlapping subproblems, these two properties are satisfied in this recursive code, then we can definitely use dynamic programming, or we say memoization, that is storing the results of the computations in a memo to optimize this code. Let's see if we find overlapping subproblems. You can see that here you can see that CC19 is computed here, CC19 is computed here again. You can also see that 18 is called here, 18 is called here, the function on 18 is called here. So these problems are repeating, and observe that we are using the results of these subproblems to find the results of larger problems. So these are the solutions of smaller subproblems, and out from these solutions I am basically calculating the solution for my larger problem, and hence this satisfies the two properties of dynamic programming. Hence I can use this approach, hence I can use memoization to optimize the code that I have. Okay, so how I can do that? Observe that here at each level there are two things which are changing. The first is the index variable, and another is the amount. Okay, so I don't want my this pair, let's call it idx and am, this is the pair. I don't want this pair to repeat. Okay, so once 19 has been computed, I do not want to call this again, so that's why I would use a dp array. Okay, so I will use a dp array of 2 dimensions. The first dimension is index I, the other dimension is amount am. Okay, so for a corresponding index and amount, I'll store the result here, such that if the same pair reappears here in the tree, I simply return the result right from the DP table rather than computing it again and again. Okay, so that's the idea. Let's see how to improve this, how to implement this solution, this idea into the code. Okay, so this is the memoized code. So this is how the memoization will work. So I'm declaring a DP array of dimensions n cross amount. So n is the number of indices or the number of elements in the array, in the coins array, while amount is the amount that I want to generate. And here what I am doing, first at this case, if the coin that I'm standing has a value less than the amount that I want to generate, that means I can use this coin. So here for the result that is returned by these function calls, okay, I will store that result for that particular index and amount in this DP array. So this dimension is basically representing the index, okay, and this dimension here is representing the amount. So these are the 2 dimensions which we have here, and I'm taking minimum of the results which are returned here. And the last result that we have is basically do not use this coin because its value is greater than the amount that we require, and simply jump to the next denomination, and I am storing the corresponding result in my DP array for that particular index and amount. And this is the base case, which stays the same. And how this has decreased the time complexity, let's see that. You can observe that for each index and amount, once the value for a particular index and amount pair has been computed, I will not compute that value I will not recompute the value for that pair again. Okay, that means I just have to perform the computations for a particular pair exactly once. And how many such pairs will there be? If there are n such indices, unique indices, and amount goes from 1 to, let's say, a, then that's the time complexity, because these are the number of unique pairs that we would have. Unique ordered pairs, that means 1 2, if I take 1 2, it is different from 2 1. Okay, so these are the unique pairs of index and amount that we can generate, and these will be the number of function calls that we would have, and hence the time complexity. Same goes with the space complexity. Since I am using a DP array of dimensions n cross a, the space complexity will also be n cross. So that's how I improved the time complexity considerably, but at the cost of space. Okay, so I'm using extra space, but I have reduced the time complexity. Will this work for the problem that we have? Yes, it will work, because the constraints of the problems are the number of indices, the length of the coins goes up to 12, and the amount goes up to 10,000. So 12 into 10,000 will work fine for the judge limit, that is 1 second. Okay, so that's how the memoization work. Let's see another approach. Since we are using dynamic programming, we have 2 approaches of dynamic programming. First is memoization, and another is building the solution in bottom-up manner. So in bottom-up manner, what happens is we have our DP array declared, and we have the solutions for the smaller problems, and from the solutions of those smaller problems, we generate the solutions of larger problems. Okay, so we keep two pointers. The first pointer iterate over the indices. So basically we are simply iterating over all index amount pairs. So we are checking for all I index amount pairs. For that I'm using two pointers, the pointer I, which iterate over all indices, namely the corresponding indices of the coins, and a pointer j, which iterate over the amount starting from 1 to the amount that we are given here, amount. That's what this pointer is doing. Okay, so what I'm saying, okay, use this index, start from the coin number 1 or coin number I, and ask whether we can generate j from that coin or not. If the coin that we are currently standing has value less than the amount that we want to generate, then that means this corresponds to the case that we discussed here. Okay, and hence we can update our DP array using the results of the previous results which were computed before. So these are the results which are already computed in the DP array, and I'm simply using those results. So DPI j minus coins I minus 1, this represents, okay, I am standing at index I, so I'm using the denominations from index I to n minus 1, from I to n minus 1, and the amount that I want to generate is j minus coins I minus 1. So I'm not using this coin yet, but it is saying, okay, I want to use this coin. Okay, so initially the amount is, so I want to generate j. Okay, so j minus coins I minus 1 is already generated, and this represents the number of coins to generate that amount, and using this coin will increase the number of coins by 1. So that's what I'm doing here, while in this case I'm not using that coin, so hence the number of coins is not increasing. Otherwise, if the coin that I am standing upon has value which is greater than the amount that I want to generate, that simply means I cannot use that coin and hence jump to the next coin. So that's what this result is doing. Finally, the result will be present at last index and for and at n cross m, at nm here. Why? Because here what it's saying, okay, I have generated the amount with the denominations, with the n denominations that we are given. Okay, and hence I'm returning the result from here. The time complexity for this solution is same, that is n cross a, which was there for memoization, and same is the same goes for the space complexity, that is also n cross a here. Okay, so that's all for this video. This was a simple problem. I hope you understood that, and let me show you the code implementation of this problem in, okay, so this is the implementation for coin change problem. Okay, so this is the base case. Here the index, this is the base case, index is crossing the size of the array, amount has reached the, we have generated the amount. Okay, and this is the condition where we are checking whether the amount that we want to generate is less than or equal to the coins, and this is the final case where we can use that coin. Here I cannot use that coin, here I can use that coin. And this is the code in C++, this is the implementation in Java language, and this is the implementation in Python language. I have attached the code in the description, so make sure to check it out. If you have any queries, then please ask in the comments. Thank you.